you so much. So thank you so much, first of all, for this invitation to speak today to you all. I have just checked the number of participants. We are at 107. This is really smashing. So, and many of those, or several of those are actually, several of those I know. So hi to everyone, those who know me and those who don't know me. So I'm really very honored to be here and speak to you today about topics dear to my heart. And you will have to forgive me that I now and then dive deep into the theory that is behind this. However, I'm more than happy to answer all questions that you may have. And I understand that they are taken care of a little bit in the background. So even if you're not getting to all the questions, don't hesitate to email me or us in Graz. So I want to talk about weather and climate regimes and extrasolar planets. And when I manage to move forward, there we go. Right, so this is perfect. So, and we should of course start within our own solar system. And just for giving everyone a head start, and my understanding is that we not only have hardcore astrophysicists on our call, we are living in our own solar system. We have 4 rocky planets orbiting very close to our host star, the sun, and we have 4 gaseous planets, and this will come in handy to remember that later on. So this is where we start out. We of course believe we know very well our solar system, but we all are aware that there are a lot of open and exciting questions. Our solar system is located in the galaxy, which we are calling Milky Way, and we are sitting somewhere out here at the outskirts at one of the outer spiral arms. And only in this vicinity it is that we have studied our immediate surrounding with respect to other planets, so-called extrasolar planets outside our solar system. And these about 4,300 extrasolar planets are located in about 3,900 planetary systems. Does everyone see my cursor, by the way?
Yes, we can.
Okay, perfect. Thank you. And the big surprise that we were in for was that none of these extrasolar planetary systems was even comparable to our own solar system. So that means not even did we not find any sibling of the planets we know from our solar system outside our solar system, so in the galaxy. In addition to this, all the extrasolar planetary systems do not compare to what we know from our solar system. And here's one example. So this is the poster child for not being our solar system, namely TRAPPIST-1. TRAPPIST-1 is an M dwarf. It's a very cold small star. And if you see down here, we have the inner solar system with our 4 rocky planets, Mercury, Venus, Earth, and Mars. And within the orbital space of Mercury in our solar system, TRAPPIST-1 would fit. On top of this, this low luminous M dwarf is orbited by 7 rocky planets. And of course, we are immediately seeing this beautifully green ring around in the solar system and also in TRAPPIST-1, which then of course moves towards the idea of may there be habitable planets. We will dive into this a little bit later on, and I'm sure many of you are aware of this, but this is just one of the extrasolar planetary systems, which is very, very different from what we know. Now, let me make the last point of this introduction, namely, if we think of 400 billion stars forming our own Milky Way, our own galaxy, and if each of those stars would have at least one planet orbiting itself, then we would look at an ensemble of more than 400 billion planets in our own galaxy. And now we not only have one galaxy, we have many galaxies. So there is a huge amount of planets, of extrasolar planets out there, of which we haven't found any Earth sibling so far. Of course, there are debates out there that we have found that we are very close to find an Earth sibling, but I'm a little bit hesitant to claim this here. Right, let's see what else we know, what else we have learned about extrasolar planets. So setting the stage. From the, now can I move to the right? Yes, from this 5,300 planets, we do not know too much in detail about those. But if we are but for a subset of 1,170 about, we know the planets and the orbital distances, and this is what I'm showing you in this plot. So we have on the y-axis the planetary mass, on the x-axis the orbital period, and just to guide your mind a little bit, for Earth it would be 1 year. And not for all of the exoplanets we know these details. So but we would like to know them in order to understand more. Where do we go? So, and if I'm now overplotting in color the temperature of the host star, then we complete our picture a little bit. So the color bar here on the right-hand side is the host star's temperature, and I've indicated the temperature of the sun, which is here. And you see that many of the big, or of the massive high mass planets seem to be linked to stars with higher temperatures. And we can now even add another layer of information. I know this becomes crowded, but you see how the picture actually emerges. I'm overlaying now the size of the planets. And what I want you now to recognize is that in particular, the massive planets, so we are here this is about 1 Jupiter mass. So the massive planet seems to be particularly large if they orbit hot or very warm, very hot host stars. So red means they're orbiting that they have a very hot host star and they have a very large radius. So what we are seeing here is that we have a substantial fraction of the known extrasolar planets which actually are not just rocky, but which have an extended atmosphere. And that's the kind of planets we are diving into because one of the reasons for this is we have a quite good amount of observational data for those. And of course, I have to quote JWST because it brings us the next leaps in our understanding for extrasolar planets. And I'm moving on into showing you some of the first data we have seen for a particular gas giant, which is called WSP-39. The specifics don't matter. What I'm showing you here are early release science data. And JWST has a very specific way of observing extrasolar planets. It basically uses the so-called transit technique. And I'm showing this here in this little sketch up here. So we have a host star in front of which our planet passes by, and we would stare at a particular wavelength, at a particular energy. We would stare at a star-planet system and see how the flux, how the number of photons in that particular wavelength dip down. And then when the planet leaves the stellar disk, we are back to the original level of flux, of photon flux from the star. Now, this is a very simple experiment, but it becomes complicated because we wish to move towards the infrared, so towards larger wavelengths. So let's look at the left-hand side of this slide. Here we have the number of photons plotted for quite a wide wavelength range, for 0.46 to 5.7 micrometers. So we are already well into the infrared. And what we wish now to measure is actually how deep this depression goes depending on wavelengths. And that's what we're going to do here. Don't worry, I'm putting this up slightly bigger in a moment. Now what we are doing here on the right-hand side in this plot, which says at the x-axis, at the y-axis transit depth, we are measuring the depth. So there we are. We're measuring the depth of each of these so-called transit light curves and put them up in our wavelength plot. So we have on the x-axis the wavelengths, and if you are now looking at 5 micrometers, so this would be about 6 micrometers. Okay, about this this light curve, and we put down our measurement here. And I have indicated this here for the optical wavelength. So this is actually the measurement we are putting down in this figure. So why do we do this? Well, because these light curves do tell us something about the chemistry, about the chemical composition of this atmosphere. And this is what we are discussing now here on this plot. So again, all these dots with error bars are the measurements of the transit light curves that we have obtained with the JWST. And now, luckily, the authors of this paper have been so kind to indicate in color which molecule may contribute to this particular absorption features. So in light blue, we have, what do we have? Yes, in light blue, of course, we do have water. In purple, we have CO2. In olive green, we have H2S. But there are also, of course, some of you may have followed the literature. There was also a surprise for the community into this, and this is this little bump. This is SO2, and for now, it's actually it's a big mystery for now why SO2 is there. And one of the arguments is we are probably looking at photochemically driven reactions. Okay, so this is what we get from from instruments like JWST. But what we actually would like to know is why we are seeing this chemical composition. So is this now typical for the planets we are looking at, or is this specific? Can we learn something about it? And you also may have spotted the word clouds on this slide, and you see it's associated with a horizontal straight line, which always wrenches my heart, because this means we don't have much information about clouds in these atmospheres. So what do we need to do? What are we doing? Well, we are constructing what I would call virtual twins for extrasolar planetary atmospheres. And our approach is really constructing extensive models, complex models that help us to understand exoplanetary atmospheres through virtual twins. And there are 3, maybe 4 big aspects that we need to look into. And I'm not putting up any equations now. For now, I just want to transport the concept of what we need to understand in order to understand, for example, JWST observations and figure out what these atmospheres are made of. There's, of course, the big part of the gas phase chemistry. And here we are wishing to be able to predict the chemical composition of each of the atmospheres, depending on their host star, depending on the origin of this planet. This, however, is affected by the cloud formation, and I will say a little bit later on about this, because this is basically a phase transition where we are depleting the local gas phase by all elements that are condensing. So there is a strong feedback on the gas phase, obviously. Then we also would like to know how energy transport works in the atmosphere. So we have looking at extrasolar planets, which may or may not be heavily irradiated by their host stars. And this, if we think about transport processes in atmospheres, then causes triggers or causes winds, strong transport of material around the planet or into the deeper atmospheres. So these 3 complexes, gas phase chemistry, cloud formation, energy transport, for example, by radiative energy input, and then the movement, the transport of matter is actually what shapes these atmospheres. And I will go into some of the results in the following slides. Right. So with our virtual twins, we wish to explore systematically exoplanetary climate regimes. And one of the big input properties comes, of course, from the radiation field from our host star. So we have cold and faint. We will look at cold and faint host stars like the M dwarf that we had in the TRAPPIST-1 system. But we will also have warm and luminous host stars, like, for example, our sun. Now, our sun is not particularly warm and luminous, but it's doing a good enough job for really roasting some of the exoplanets. And one of our other parameters is then the distance from these host stars, which I have phrased initially as orbital period. So let's jump into the results to give you a bit of a picture. So yes, as we getting closer to the host star, we will expect that the planet becomes hotter. So what are the parameters? Host star, we have cold and faint host stars, warm and luminous host stars. We're moving our planets closer or further away from the host star. If we move closer to the host star, we will expect that the planet becomes globally hotter. Right. So, and this is now where we are utilizing our virtual laboratories to really study climate regimes. I know this is maybe a little bit overwhelming for some of you, but just bear with me. I will talk you through this, and hopefully we walk out with a bit of a picture of how different planetary atmospheric climate regimes may be. So on the left-hand side of this plot, we have faint cold host stars. So this is the M dwarf, here with a K5, G5, and then an F5 host star. So on the right-hand side of this plot, we are always orbiting a warm, luminous star. If we go down this plot, we see that the global temperature, so here on the left-hand side, I'm always listing a global temperature for our host star. So we're basically averaging over all potential asymmetries. That means up here we have always the cold planets, and down here, if we go down, we are moving closer to the host star, so the planet receives more irradiation. That means more external energy. So that means our host stars, our planets become warmer. Now let your eye rest a little bit in the upper left corner, because here you see that this cold planet, which orbits an M dwarf, which is rather far away from its host star, has a rather homogeneous temperature distribution in its atmosphere. And if you follow my cursor now down to the right-hand side corner, you see how the temperature structure becomes more and more different between the day and the night side. On the right-hand side, we have the day side. On the left-hand side, we have the night side. Now this looks all still quite calm, but if we move on, and if we move our planet even closer to the host star, the day-night side differences become more and more pronounced. So you see, we are now looking at really hot, really non-terrestrial environments. So we are having a global temperature of 2,600 Kelvin, which is insane, which also means that we will have a very strong day-night difference. So that means down here at the very bottom, on the right-hand side of this plot, we have the hottest planets, which have the strongest difference between the day and the night side. Okay, so this is kind of the global overview, and I will now pick three particular classes such that we can dive a little bit more into what this actually means. So what I'm now doing, I'm now using really our computer codes, our virtual laboratories as virtual twins for three of these planets in order to understand more about what is going on in these planetary atmospheres. We can also turn this around and say that we are using our virtual laboratories as virtual twins to forecast weather and climate on extrasolar planets. Oh, this is in German, I just see, I do apologize. Okay, so we have here a temperature map for a cold planet, for an intermediately warm planet, and for a pretty hot planet. Each of these maps shows us the temperature structure in these atmospheres, and we are slicing through the equatorial plane and look from the top onto this planet. Let's start with the hot planet on the right-hand side. So we see that we have an extreme temperature of about 2,400 Kelvin on day side, and of about less, I know it goes down to 400 Kelvin on the night side. The low night side temperature remains the same for all the three cases, but we now also see that the colder planet will remain cold on the day side. What else can we learn from this, from our virtual laboratories? Well, one of the aspects that we are really keen to understand is cloud formation and how it affects the local chemistry. And therefore, I'm now showing you, without any further detailed explanation, the distribution of cloud particle sizes. And for you now, I want you to focus on this lower right-hand side plot, because you see that, because this very nicely visualizes that only on the night side for the super hot planets, clouds would emerge. So we would then expect a cloud-free day side. And if you now wander back to our cold planet, by basically moving the planet away from the host star, we see that we have the entire atmosphere covered with clouds. All right, what else can we learn? And now I'm really diving into the climate and weather regimes, and I have made a couple of categories: cloud coverage, element depletion, and we leave the mean molecular weight for now, but also the thermal ionization. And I'm aware that these are very much physically oriented categories, and I hope you forgive me because I am a physicist, so I'm really drilling down into what we are seeing. We have 3 climate regimes, which we called the cold planet, the transition planets, and then the hot planets, and you will see why we are going for this. In the cold planet regime, we have a very homogeneous, for our perception, a very homogeneous temperature distribution and cloud coverage. You of course see that there are differences because the temperature profile changes into the planet, and there are also slight differences between the day and the night side. But for the climate regimes we are looking at right now, this is really the poster child for homogeneous cloud coverage, and then with that element depletion. The hot planets, as I explained, are extraordinary hot. We have a temperature difference here of about 2,500 Kelvin. So there is no surprise that we have no clouds on the no clouds on the day side and only clouds on the night side. Let me jump forward. We also like to talk about the thermal ionization, and the reason for this is this allows us to discuss eventually how a magnetic field may couple and may shield the exoplanetary atmosphere from erosion by the host star. And you may, of course, extrapolate the thought further. If we have a well-coupled atmosphere, we potentially may have a better shielding of whatever is going on in the atmosphere. So therefore, yes, let me go to the conclusions for this slide. So therefore, for the very cold climate regimes, we have a chemically homogeneous and geometrically symmetric atmosphere, while we have for the hot planets, we have a very strong chemical day-night difference, but we also have a geometrical day-night difference because of the hotter temperatures, the day side will be considerably more extended than the night side. And as you are aware, JWST is searching for this geometrical asymmetries. What is more, we need to begin to think about deep magnetically coupling of the day side, and also in how far this affects the interior of the planet and the evolution. Right, so this is a little bit the hardcore version of how we are using our virtual twins. And I would like to move on to some thoughts on aerial biospheres, because I'm well aware to what audience I'm talking here too. So I'm not asking for forgiveness to put up a rather loose definition of aerial biospheres, but I just invite you to dive with me into this sort of translucent area of research, shall we call it. So an area biosphere I would define as an ensemble of small particle surfaces suspended in an atmosphere onto which water could condense, and also on which either also or biomolecules may form. And of course, this whole story of area biospheres has been triggered by the Nature paper by Jane Reeves on the detection on phosphine in the Venusian atmosphere. At the time, these observations were based on ALMA detection, and ALMA is a millimeter, observes in the millimeter regime, so which is intrinsically challenging, and it had been backed up by observations from the James Clerk Maxwell telescope. Meanwhile, the absolute amount of the flux measured has been readjusted, so that one is discussing still the presence of phosphine, but not anymore at this very high level. What I nevertheless like with this paper is that it has spurred our scientific imagination and curiosity about looking into potential chemical paths to form, in this case, phosphine, and then, of course, later on also other fingerprints for biological activities in not so terrestrial environments, I shall call it. And I would like to cite that paper because I think they have very, in my perception, they have very carefully worded or very carefully put out their ideas. So they said pH3 could originate from unknown photochemistry or geochemistry, or by analogy, from biological production of phosphine on Earth from the presence of life. So, of course, no one is debating the presence of life in Venus, in the clouds of Venus, but many people have used it for readdressing readdressing potential habitable environments in non-so-terrestrial situations. So why was that interesting for Venus? Now, we probably don't need to visit the idea of habitable zones. So this is the habitable zone for the solar system. Of course, the Earth sits right in there, Mars sits at the outskirts, and Venus sits just inside. And the idea behind this paper was that they realized that the phosphine seemed to be attributed to a cloud layer around 53 to 61 kilometers, which would sit at 0.5 bar and had a gas temperature of 30 degrees Celsius. So forgive me, we are jumping between the unit systems now. And the challenge was, of course, obvious, and they received a huge amount of criticism from the community. Nevertheless, the challenge was that, of course, we all knew that Venus has a very high acidity. And discussions went as far as debating how to define acidity, etc., etc. I will not go into this. It is just for us to realize that, of course, this community knows that for us astrophysics, that there is probably more out there for us to be aware of. Now, Sarah Seegers has picked up this idea of, or has revisited this idea of clouds as biospheres, and I'm just repeating this here again because I think it's actually quite a nice concept which feeds into many of our ideas about cloud formation, of course. So the cloud layer, the Venus cloud layer, from which the Greaves et al. Papers suggest that this phosphine may originate, is located, as I said, a little bit above 60 kilometers. No, where are the kilometers? Yeah, here, a little bit below 60 kilometers. And the temperature seemed to be too high for normal biological activity to sustain. The idea they have been putting forward is that acidic droplets do exist higher in the atmosphere, or higher in the cloud layer, sorry, where it is colder, and there some potentially extremophile microbes may survive. As we are looking in a gravitational dominated environment, these cloud droplets will drop down towards higher temperatures where the water will evaporate, but these spores would then or are suggested to survive in this hotter lower layers, from which they then get dragged up again into colder environments where they then find water to strive in again. Now, why I'm interested in this is because this is exactly the same thinking we have developed for cloud formation processes. So there may be a little bit in it. There may be some value in looking deeper into also cloud formation systems, really in the cloud formation processes, to potentially contribute to this idea of clouds as biospheres. Of course, not in our in the category of our superhot planets. Now, we have been now moving a little bit into the solar system, and these are, as I already mentioned earlier, very specific planets and very, earthy planets still. But the diversity of extrasolar planets is huge. And here I'm still dwelling in the gas giant regime, but we actually should have put up the rocky planet regime, which is as diverse, in particular chemically. And what we also have that adds to the diversity is the diversity of extrasolar of the host stars for extrasolar planets. Now, most of the planets that have been detected are around orbiting M or at least at the latest F stars, so the diversity is not too huge. But nevertheless, we already see here on this plot that there is much that we should look out for a more general theory of planetary atmosphere chemistry and planetary cloud formation. And this is where I'm moving into in the last couple of moments. I know I'm aware I have been a little bit provocative, and I will continue to be so, because now I will move us into approaching mineral cloud aerial biospheres. And for this, I want to go a little bit into cloud formation, just for setting the stage. So why do we need a universally applicable set of ideas? Well, the reason for this is that also due to the evolutionary processes of planets and to the formation process of planets, planets will have different sets of element abundances from which they form and which they are made of. And this is then also reflected in the atmosphere. So that means we better make sure we understand our basic processes. Therefore, if we are looking at a planetary atmosphere, we will start out with a gas phase. This gas phase has a certain element composition. It may be more silicon oxide rich compared to Venus and Earth, for example. So from the gas phase, we form cloud condensation nuclei. This is something we call nucleation. I will again not go into the details. I will just try to transport the major ideas. So from the gas phase, we form cloud condensation nuclei. On these cloud condensation nuclei, many other materials can condense. And the reason for this is once these cloud condensation nuclei form, many other materials are already thermally stable and very quickly grow a substantial bulk of this onto this cloud condensation nuclei by gas surface reactions. Now, this all happens throughout a temperature gradient. This means as these processes proceed, the chemical composition will change, and as these particles fall into the atmosphere and evaporate and return their material to the gas phase. What I'm after here, however, is that this is only the so-called, this is what I only would call the chemical part of it, but the moment these particles have formed, they gravitationally settle and fall into the atmosphere, change their material composition, release materials, and then also cause an element depletion gradient. And now we are feeding back into what we have seen from the paper by Sarah Siegers, namely that there is material transport mechanism also in the other direction. We have convectively unstable atmospheres. You may think about Hadley cells, which transport not only elements but also cloud particles high up in the atmosphere. Okay, so these are the some basic processes that we would need to look at. But what we also now know, and this is why I needed this process set up, we can predict the chemical composition of these cloud particles. And one of the species that one may consider or that does condense is iron sulfide. And for example, one of these cloud particles may have, for example, 10% of them, 10% of the material may be made of iron sulfide in a matrix of magnesium silicate oxides, for example, that is contributing by 60%. So this is definitely a fact. But what we now can explore, in particular for the colder planets that we have been looking at, because they also extend their atmospheres towards colder environments, we may hypothesize that that's some sort of extremophile, the so-called chemolito autotrophs, may harness chemical energy from exactly this iron sulfide chemistry. And here are two reactions which may contribute to this. And we have done a couple of little estimates with one of the students, which actually shows that this could work. However, for now, I really would not see this perceived as a fact, but rather as an hypothesis, which I would invite this community to look into. The facts that we certainly can deliver is in which atmospheres, what materials condense into cloud particles, which then may be seen as, or may produce some aerial biosphere later on. However, planetary atmospheres are never easy. There is again the effect of the host star through to the effect the impact of UV radiation, for example. This UV radiation, of course, opens the entire host of carbohydrate chemistry, which I'm not going into yet into for now. What I would like to place as a last idea with this crowd here is that a fact is that we have photoionization going on, in particular in the upper atmospheric regimes. But what we also know that these high energy photons may ionize our cloud particles, and then it can be shown that these charged cloud particles actually enable the formation of complex carbohydrate molecules, and one can indeed show that also the formation of glycine may be fostered on the surface of such, in this case, mineral cloud particles that previously have been ionized, for example, by high energy radiation or also by collisional processes. So with this set of challenges, I would like to stop here and really take questions. So I have led you through the complexity or to the large diversity of extrasolar planets, have shown you how we are using our virtual laboratories to study weather and climate regimes. Some of them are extreme, some of them are less extreme, and I would suggest that in particular the less extreme, colder climate regimes may be a good research ground for actually diving a little bit more into how far aerial biospheres may actually contribute to either false positives or to positive fingerprints for potential bioactivity. But of course, we have to be a little bit careful in our explorations of these processes. Thank you for your attention, and I'm happy to take questions.